Hello, all. Welcome to another lecture of the Regression Analysis course. In this video, I'm going to introduce the multiple linear regression model. So let's start. Imagine we have this data set with 6 students. For each student, we knew their exam score and how many hours they studied. Now, if I asked you to build a model that could predict a student's exam score based on how long they studied, what would you do? You would fit a simple linear regression model because you have one independent variable, that is study hours, you have a dependent variable, exam score. And so our model would look like y is equals to beta naught plus beta 1x plus epsilon error term. And now we know how to create a simple linear regression model. We have seen how to find the value of these betas, beta naught and beta 1, using different methods. In particular, we saw ordinary least squares estimation method and maximum likelihood estimation method. Perfect. So given a data set where we just have one independent variable and one dependent variable, we can create a model. We can create a simple linear regression model over there. But now, what if we start adding more predictors in the model? Say now you have this data set, the same data set which has exam scores and study hours, but now you add another independent variable which is the exam anxiety. So now let's say in addition to study hours, we also know whether the student was anxious during the exam or not. We have another independent variable, how many hours they spent on social media. Another variable, that is their attendance percentage during the semester. So now we have more than one independent variable in the model. This means we are stepping into the world of multiple linear regression. Multiple linear regression refers to a statistical technique that uses two or more independent variables to predict the outcome of a dependent variable. Here, the dependent variable is still the same. The exam score we have on the extreme left, this variable is still the dependent variable. But now we have more than one independent variable. We have an independent variable study hours, exam anxiety as another independent variable, and we have two other independent variables, that is social media usage and attendance percentage. And whenever we have more than one independent variable, now we will have to create multiple linear regression model. But before we go further, there are two really important things to be careful about. The first one is each independent variable should be meaningfully related to the dependent variable. If a variable has nothing to do with the outcome, including it in your model adds no value. In fact, it can lead to a problem called overfitting, where the model captures noise rather than meaningful patterns. So given this data set to us, we should know whether the dependent variable, which is the exam score, is it really related to all the other independent variables present in the model or not. Otherwise, we will have a problem of overfitting. And the second thing is that the independent variables should not be highly related to each other. If your predictors are strongly correlated with another, the model runs into a problem called multi-collinearity, which can distort coefficient estimates and make interpretation unstable. For instance, in the same data set exam score, we should be careful about the multicollinearity. That is, the independent variables present in the data set should not be related to each other. So the ideal case would be the dependent variable is strongly related to each independent variable, but the independent variables themselves are not strongly related to each other. And how to deal with these two things, we will talk about this in the coming video. So now we are not going to talk about the model where we just have one independent variable. Rather, we would talk about the situations where in general we have, say, p number of independent variables present in the model. Say we have a dependent variable y and p independent variables denoted by x1, x2 till xp, and They are related to the dependent variable through the parameters beta naught, beta 1, beta 2 till beta p. Therefore, the multiple linear model would look like y is equals to x beta plus epsilon. And now let's explore how to write the matrix representation of this multiple linear regression model. So we have the model y is equals to beta naught plus beta 1 x1, so on and so forth till beta p xp plus epsilon. Hypothetically assume that you are an experimenter who conducts an experiment n number of times. The first time you conduct an experiment, you would have a value of the dependent variable y1 related to the p predictors. And how is it related? It is related linearly. So we have y1 is equals to beta naught plus beta 1 x11. X11 is the value of the first independent variable for the first observation, plus beta 2 x12, where x12 is the value of the second independent variable for the first observation. So on and so forth till beta p x1p, where x1p is the value of pth independent variable for the first observation. And when you are conducting an experiment, you say that every time you conduct an experiment, you have some sort of noise in your data. So you have this epsilon 1 noise when you conduct the experiment first time. And when you conduct this experiment n number of times, you would have these n equations. And we can write these n equations in the matrix form this way. And whenever we deal with multiple linear regression model, we will usually write things in a matrix form because matrix notation helps us write things more compactly and also take advantage of linear algebra tools to compute estimates and analyze variance. When we started with the simple linear regression model, the first thing we did was to make some assumptions on error term. The first assumption we made on error term was the epsilon I, the error we have from each observation, its expectation is equals to 0. The second assumption we made is that variance of each epsilon I is a constant, and we gave that constant a notation sigma square. The third assumption we made is that all EIs are independent and identically distributed, and the distribution they follow is a normal distribution. These are the assumptions which we made on error term, which we made on single error term, random variable epsilon I. In this video, we are going to generalize these assumptions for random vector error term. So let's start by generalizing the first assumption. The first assumption we have on error term is if we have n observation, then the expectation of epsilon 1 would be 0, expectation of epsilon 2 would be 0, so on, expectation of epsilon n would also be equals to 0. Let's try to generalize this assumption and see what would be the expectation of the random vector error term epsilon. So this is the matrix form of the random vector epsilon. Epsilon is the n cross 1 vector of random errors, and if we take expectation both sides, then on the left hand side we would have expectation of the random vector epsilon, and on the right hand side we have expectation epsilon 1, expectation epsilon 2, so on till expectation epsilon n. Now what is the assumption on single random variable epsilon I? That expectation of each epsilon I is 0. Therefore, each entry of this column vector would be equals to 0. And we have that expectation of this random vector epsilon is also equals to 0. And this is what we get when we generalize the first assumption made on epsilon I. Let's generalize the second and the third assumption on error term. The second and the third assumption on error term is that the variance of each epsilon I is constant, denoted by sigma square, and all EIs are independent and identically distributed. Before we generalize it, let's see the formula of variance of a random vector x. So when we talk about random vector x, it's no more a variable, it's a matrix, it's a column vector x, and its variance would be equals to expectation of matrix x minus its expectation times matrix x minus its expectation whole transpose. This is the formula of variance we have. But what we are interested in is finding the variance of the random vector epsilon. Variance of epsilon would be equals to expectation epsilon minus expectation of epsilon times epsilon minus expectation of epsilon whole transpose. We just saw the generalization of the first assumption on error term, that the expectation of error term epsilon random vector is equals to 0. If we use this assumption in this equation, we get that variance of epsilon is equals to expectation of epsilon minus 0 times epsilon minus 0 whole transpose, which gives us variance of epsilon is equals to expectation epsilon times epsilon transpose. Now let's try to look at the variance covariance matrix. Variance of a vector is equals to covariance of that vector with itself. And here this vector epsilon is a column vector with entry epsilon 1, epsilon 2, epsilon 3, so on till epsilon n. And we are trying to find the variance covariance matrix of this vector epsilon with itself. And in the first row, we would have the covariance of random variable epsilon 1 with all the other variables. Therefore, the first entry would be the covariance of epsilon 1 with itself. The second entry would be covariance of epsilon 1 with epsilon 2. The third entry would be covariance of epsilon 1 with epsilon 3, so on till covariance of epsilon 1 with epsilon n. In the second row, we would find the covariance of epsilon 2 with all these epsilon 1, epsilon 2 till epsilon n. Therefore, the first entry in the second row would be covariance of epsilon 2 with epsilon 1. The second entry in the second row would be the covariance of epsilon 2 with epsilon 2. The third entry in the second row would be the covariance of epsilon 2 with epsilon 3. Then it will continue till covariance of epsilon 2 with epsilon n. In the third row, we would find the covariance of the third variable epsilon 3 with all the other variables epsilon 1, epsilon 2, epsilon 3 till epsilon n. We will continue doing this, and in the last row, we would write the covariance of epsilon n with all the other variables, which would be covariance of epsilon n with epsilon 1, covariance of epsilon n with epsilon 2, so on till covariance of epsilon n with epsilon n. And we have the variance covariance matrix. Now look at the diagonal carefully. The first thing we have is covariance of epsilon 1 with epsilon 1, covariance of epsilon 2 with epsilon 2, covariance of epsilon 3 and epsilon 3. So if you move along the diagonals, we have the covariance of a variable with itself. And now we use a property of covariance, that covariance of a variable with itself is equals to the variance of that variable. And therefore, all along the diagonals, we would have variance of epsilon 1, variance of epsilon 2, variance of epsilon 3, and the last entry in that diagonal would be variance of epsilon n. And we have this matrix. We had an assumption that variance of each epsilon I is equals to sigma square. And in the diagonal, we have variance of epsilon 1, variance of epsilon 2, variance of epsilon 3. So we replace this variance because we use the fact that variance of each epsilon I is equals to sigma square. We use this assumption, and all along the diagonals we have sigma square. And for non-diagonal entries, we use the assumption that each EIs are independent, because if all EIs are independent, then the covariance of EI and EJ when I is not equals to J would be equals to 0. And if we use this assumption, we have that all the non-diagonal entries would be 0. And this is what we would have. We would have variance of the random vector epsilon is equals to, in the diagonal we have sigma square, and all the non-diagonal entries are 0. Now we use a property of matrix and we can factor out sigma square. When we factor out sigma square, in the diagonal we would have 1 and all the other entries would still remain 0. And we have variance of random vector epsilon is equals to sigma square times this matrix where we have 1 in the main diagonal and we have all the non-diagonal entry to be equals to 0. And what is this matrix? This matrix is the identity matrix. And the dimension of this identity matrix would be n cross n because we are trying to find the variance covariance matrix of random vector epsilon with epsilon. And epsilon is the n cross 1 vector of random errors. Therefore, the identity matrix we have over here has dimension n cross n. And we have the generalized assumption on this error term that variance of this random vector error is equals to sigma square times the identity matrix, where the dimension of this identity matrix is equals to n cross n. Let's talk about the distribution of this random vector error term. We have the assumption on each epsilon I that all epsilon I have same distribution, have identical distribution, and this distribution is normal. And this random vector error is a column vector of this epsilon 1, epsilon 2, epsilon 3, so on till epsilon n. And since all epsilon I have normal distribution, therefore this random vector epsilon will also have normal distribution. And thus, we have the generalized assumptions on this error term. The first generalized assumption is that the expectation of random vector error is equals to 0. The variance of random vector epsilon is equals to sigma square times identity matrix. The third assumption is that this random vector epsilon has normal distribution with mean 0 and variance sigma square times identity matrix of dimension n cross n. When we are dealing with multiple linear regression model, we make one more assumption on the model that the rank of the X matrix is equals to P plus 1. And why do we make this assumption on X matrix? We are going to talk about that in the next video. But for now, all I can tell you is this assumption we have on X matrix is pretty important. Let's quickly look at the consequences of these assumptions on multiple linear regression model. Say we have y as a dependent variable with n observations and p predictors, and the model would be y is equals to x beta plus epsilon. If we use the first assumption that expectation of epsilon is equals to 0, its consequence on the dependent variable would be that expectation of that dependent variable is equals to x beta. The second assumption we have on random vector epsilon is that variance of this random vector epsilon is equals to sigma square times identity matrix. Its consequence on the dependent variable y would be that variance of y would be equals to variance of x beta plus epsilon. We are treating x as a fixed quantity and we do not know the value of beta as of now. But once we know the value of beta, it is not going to change as you move from one observation to another. Its value would be fixed. And we treat this x beta quantity as a fixed quantity. Variance of a fixed quantity is 0. Therefore, variance of y would be equals to variance of this epsilon, which is equals to sigma square identity matrix. The third assumption we have on random vector error term is that it has normal distribution. As a consequence of this assumption on dependent variable, we would have that the dependent variable would also follow normal distribution, because x beta is being treated as a fixed quantity and the variation in y we have is because of the variation in the epsilon term. Therefore, if epsilon term has normal distribution, as a consequence, y will also have a normal distribution. And the mean of this dependent variable y would be x beta, the variance would be sigma square identity matrix. Once we have the consequences of the error term on the dependent variable, we have multiple linear regression model, which is the generalization of the simple linear regression model, where we express the mean of the dependent variable as a linear function of multiple predictors present in the data set. So now if we have p predictors in the model, then expected value of y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth till beta p xp, where xi's are the predictors, they are the independent variables present in the data set. Betas are the regression coefficients, the parameters, the coefficients of all the independent variables we have, plus an intercept beta naught. And the quantity on the left hand side, which is E of y, is the mean or expected value of y for a given value of x. And now our goal is to find the value of these regression coefficients. And that's what we're going to see in the next video. We will see how to find the value of these regression coefficients using ordinary least square estimation method.